Hello everyone, welcome back to this online class. Today we are going to look at non-homogeneous linear ODEs of the second order, and in particular we are going to look at Cauchy Euler equations. Now we are given this question. We are asked to solve the following differential equations. In part A, we have x squared times d squared y over dx squared minus x times dy dx minus 3y is equals to ln x over x. In part B, we have x squared minus this x squared times d squared y over dx squared minus 5x dy dx plus x 8y is equals to 2x cubed ln x. So those are Cauchy Euler equations. To be able to solve them, remember, when we talk about Cauchy Euler equation, is an equation with the variable coefficients of the form that you can see in those two problems. Now, to be able to solve them, we first of all need to reduce it to an ODE with the constant coefficients. So what we always do is that we let, where we have x, we are going to let that to be exponential t. So that if I make t the subject from here, it means that t will be equal to ln x. So we are using a change of independent variable. Now, when I differentiate this equation with respect to x, from here it means dt dx is equals to 1 over x. So with this change of variables, you're going to find that where we have dy over dx, if I use chain rule, it's the same as dy over dt times dt over dx. And so this will give us dy over dx. If I replace dt over dx by 1 over x, we're going to get 1 over x dy over dt. Or if I multiply both sides by x, we are going to get x dy dx is the same as dy dt. So that's how we transform the first derivative, that where we have the product of x and dy dx, that should give us dy dt. What about the second derivative? Let's see how to transform it. D squared y dx squared. You see, this is the same as derivative with respect to x of what we got in the first derivative, that was dy dx. That's how we write that in the second derivative. And so I can replace dy dx by dy dt. So this is the same as, let me write is equals to. So that's the same as derivative with respect to x of our dy dx. We got 1 over x times dy dt. So I can now use product rule to differentiate this. So this you can as well write as, I want to keep 1 over x constant, 1 over x constant, differentiate dy dt with respect to x, so this d dx of dy dt. Plus now differentiate 1 over x, we are going to differentiate 1 over x, keeping dy dt constant. And so this can as well be written as 1 over x. I want to use chain rule, derivative with respect to t of dy dt times dt dx, that's chain rule. Then what's the derivative of 1 over x? That's the same as negative 1 over x squared. When you differentiate 1 over x, you get 1 over negative 1 over x squared, then times dy dt. And so how else can we write this? The one that I have bracketed, this one is the same as second derivative of y with respect to t. And remember, dt dx was 1 over x. We got it from here. So this is 1 over x, d squared y, dt squared, times another 1 over x, minus 1 over x squared, dy dt. And so you can as well write this as 1 over x squared, d squared y, dt squared, minus dy dt. Of course, there's a bracket here because I've factored out the 1 over x squared. On the left, what did we have? We had this d squared y over dx squared. So if I multiply both sides by x squared, you realize that I'm going to get x squared d squared y over dx squared. This is the same as d squared y over dt squared minus dy dt. So this is how to transform the second derivative. And so you follow the same differentiation procedure in a case where you have higher order ODEs. You can be able to transform the third derivative, the fourth derivative, etc. So just wanted to explain how those derivatives are transformed when you make the substitution that x is equals to exponential t. So instead of the variable x, we're changing to a new variable t. So now let's see how to solve part A of these problems. So part A, we need to transform that to a linear ODE with constant coefficients. So what you're going to do, where we have x squared, d squared, y dx squared, we are going to replace by what you have found there. And also you also replace where we have x times dy dx, replace with what we have found there. Where we have ln x, we have said ln x is the same as t. It's also very important. Where we have ln x, that would be the same as t. So let me rewrite part A so that I show you how to transform it. So right here, part A, we have x squared, d squared y, dx squared, then minus x dy dx, minus 3y is equals to log of x over x. Remember, x is greater than 0. Why must we have this condition? Is that when you talk of natural log, is only defined when the parameter is greater than 0. So you cannot get log of 0 because log of 0 is infinity and log of a negative number is also infinity. So we require that the parameter has to be a number greater than 0. So this first derivative will give us the whole of this one. Let me circle it. The whole of this will give us d squared y over dx squared minus, it's now over dt squared because we are changing from x to t. So instead of x, I'll write t minus dy dt. Then we have minus, instead of this one, this should give us dy dt. So this is dy dt, then minus 3y. Instead of ln x, we said ln x should give us t. What about x? X was equals to exponential t. So we change everything to t. Now let's simplify this one because I can see there are some terms which are like terms, so we can be able to simplify. this can now be written as, you can say, or d squared y dt squared minus 2 dy dt minus 3y is equals to t times exponential negative t. Now this is, you see now it is a linear ODE with constant coefficients. Now we need to solve it. We have transformed the given ODE in part A to a linear ODE with constant coefficients. This is a linear ODE with constant coefficients. Of course, it is non-homogeneous. To solve it, we have three methods. Of course, you get the general solution, which is the sum of the complementary function and the particular integral. And there are three methods of finding the particular integral. The first one is the variation of parameters. Another one is the use of inverse differential operators. And another one is the method of undetermined coefficients. So we have two solutions. So the first solution is the complementary function. How do we denote that? The YC. But before we talk of the complementary function, let's write this equation in terms of the D operator. So you can say let D, in this case it is now derivative with respect to t, so that d squared will be the second derivative with respect to t twice. So the equation in terms of the D operator will now be this one. So our ODE is now d squared minus 2d minus 3 operating on y to give us t times exponential negative t. So that's what we have. Now, Roman 1, you write complementary function. That is denoted by yc. Remember now it is a function of t. So how do we get it? You need to solve the homogeneous part of this equation, that is d squared minus 2d minus 3. This should operate on y to give us 0. And so what is the auxiliary equation? So I'll write here auxiliary equation. That is d squared minus 2d minus 3 is equals to 0. What about the roots? I can use quadratic formula. So we have two roots. d1 and 2 is negative of b. Our b is negative 2. So that is negative of negative 2 plus or minus the square root of negative 2 squared minus 4 times a is 1 and our c is negative 3. Everything you divide by 2 times a, which is 1. So this is the same as 2 plus or minus the square root. That's 4 plus 12, that will give us 16 over 2, which is 2 plus or minus 4 over 2. And so that's the same as, when you divide by 2, you get 1 plus or minus 2. So you can just say that therefore, the first root, d1 is 1 plus 2, which is 3, and the other root, d2, is 1 minus 2, and that's negative 1. So these roots are real and distinct. They are real and distinct. In a case where you have your roots to be real and distinct, how do you find the general solution? So in this case, you're going to say that yc is equals to c1 exponential 3t, remember it's a function of t, plus c2 exponential negative t. C1 and C2 are arbitrary constants. Another solution is the particular integral, which I told you there are three methods of finding the particular integral. I want us to use the inverse differential operators method. So I need to make y the subject and operate on the function on the right-hand side so that we get our particular integral. So that's equals to yp is a function of t, remember, is equals to 1 over d squared minus 2d minus 3 operating on t times exponential negative t, where we have a product of a polynomial and an exponential function. What are you supposed to do? We are going to use exponential shift rule. So right here, use exponential shift rule. So I'm going to shift the exponential function to the right, to the left, I mean, of the inverse d operators. The coefficient of t in the exponential function is -1. That's what we are calling alpha. In this case, alpha is equals to -1. So what do we do? Where we have d, you replace d by d plus alpha. So that means where we have d, we need to put d minus 1. That's what we have, because our alpha is -1. So when you make that substitution, we are going to get exponential negative t. Then here we have 1 over d minus 1 squared minus 2 into d minus 1 minus 3. This should operate on t. So let me work out the denominator so I can have this. I need d minus 1 squared minus 2 into d minus 1 minus 3. What is it equal to? So this should be equal to d squared minus 2d plus 1 minus 2d plus 2 minus 3. And so this is the same as d squared minus 4d plus 0, which I don't need to write. So that this can now be written as exponential negative t 1 over d squared minus 4d. This should operate on a polynomial t. And if you look at the denominator, you realize that we can factor out the d, so that this can as well be written as exponential negative t 1 over d times 1 over d minus 4 operating on t. So what do we do? Let's expand this in Maclaurin's series. So right here, expand in Maclaurin's series. Recall the expansion, the Maclaurin series expansion. Let us take note that when you have 1 over 1 minus z, this is the same as writing 1 plus z squared plus z cubed plus so many other terms up to the last one. And when you have 1 over 1 plus z, is the same as 1 minus z plus z squared minus z cubed plus so many other terms. So I have to write this in the form of 1 over 1 minus something, or 1 over 1 plus something. So what I need to do is to factor out -4 so that I can have 1 minus d over 4. So before I expand, this can be written as, remember I'm factoring out -4, so I'll have -1 over 4 exponential -t times 1 over d times, now it is 1 over 1 minus d over 4, operating on t. So now this is what I need to expand. It is this one. You see now it is in the form of 1 over 1 minus z. This is what I need to expand in Maclaurin's series. So when you expand, you're going to get -1 over 4 exponential -t 1 over d. Then here we'll have 1 plus d over 4, then plus d squared over 16 plus so many other terms, which will operate on the variable t, the polynomial t. So let me take t inside. If I take it inside this bracket, the first bracket, what do we have? We are going to get -1 over 4 exponential -t times 1 over d. Then now here we'll have t plus d means derivative of t, which is 1. So there we'll have 1 over 4. Because derivative of t is 1, it is d of t over 4, which is 1 over 4. What about d squared? D squared means second derivative of t. The first derivative of t is 1. When you differentiate again that derivative, you get 0. Derivative of 1 is 0. So take note that derivative of t is equals to 1. The second derivative of t will give you 0. So it means even the higher order terms will give us 0. And so there's another d operator, this one. 1 over d is the same as d inverse. So this is the same as writing -1 over 4 exponential -t d inverse of t plus 1 over 4. So d inverse means you integrate with respect to t, and so that should be able to give you, let me use another color, that's -1 over 4 exponential -t. When you integrate t, you get t squared over 2. Then the other one is plus 1 over 4t. Don't write the constant of integration. And so this is our particular integral. So you can say that our particular integral yp is equals to -1 over 4 exponential -t. Then this t squared over 2 plus 1 over 4t. And so the general solution will be the sum of the complementary function and the particular integral. So we write here that general solution is equals to complementary function plus the particular integral. Or y is equals to yc plus yp. Let me replace those functions. Let's start with yc. That was c1 exponential 3t plus c2 exponential negative t. So that's what we write here. You write or y is equals to c1 exponential 3t plus c2 exponential negative t. Now the particular integral is negative 1 over 4 exponential negative t into t squared over 2 plus t over 4. That should be 4. So plus t over 4. Now remember, this solution depends on t, but if you look at our original ODE, it was y depending on x. I need to get rid of t so that I go back to the original variable x. So you need to replace t. We said t is the same as ln x. So you can say or y is equals to c1. And what is exponential t? Exponential t is the same as x. So where we have exponential 3t, that's the same as x cubed. X cubed, remember, exponential 3t will now be x cubed. Exponential negative t, that will be x raised to negative 1, you see, which is 1 over x. So this is plus c2 over x minus 1 over 4 times x raised to negative 1, which is 1 over x. So this 1 over 4, then x down there. T is ln x, so this is ln squared of x divided by 2 plus ln x over 4. So this one here is our general solution where C1 and C2 are arbitrary constants. So that's part A. Part B, let's check the ODE in part B. What do we have? Is this one here? X squared d squared y over dx squared minus y of x dy dx plus 8y is equals to 2x cubed ln x. So I'm going to rewrite it and then again transform it to a linear ODE with constant coefficients, then solve using any appropriate method. So in part B, this is what we have. X squared d squared y over dx squared minus 5x dy dx plus 8y is equals to 2x cubed ln x. Of course, x must be greater than 0. I already explained why. So we transform this one where we have x squared d squared y over dx squared. We said this should give us d squared y over dt squared minus dy dt. That's what we should get. What about where we have x times dy dx? That's this is a negative 5. So this should give us dy dt. Then this 8y is equals to 2. What is x cubed? We have just said here that x cubed is the same as exponential 3t. What about ln x? That should be t. So we have transformed the variable x to the new variable t. Let me add the like terms. So you can say or d squared y over dt squared minus 6 dy dt plus 8y is equals to 2t times exponential 3t. Again, a product of exponential function and a polynomial on the right hand side. Let's write this in terms of d operator. Already we have defined the d, so you can say or d squared minus 6d plus 8 operating on y should give us 2t exponential 3t. So we have two solutions, the complementary function and the particular integral. So you can write here Roman 1 complementary function, which we denote by y subscript c. And we said here you need to solve the homogeneous part. Let me just write the homogeneous part here. It is d squared minus 6d plus 8 operating on y to give us 0. So our auxiliary equation is d squared minus 6d plus 8 is equals to 0. That's quadratic in the operator d. So what about the roots? I'm going to use quadratic formula so that d1 and 2 is the same as negative of negative 6, that's negative b, plus or minus the square root of negative 6 squared minus 4 times our a is 1, our b is, our c is 8, over 2 times a, which is 1. So let's work out. This should give us 6 plus or minus 6 squared is 36, then minus 4 times 8. 4 times 8 is 32. So that's 6 minus 32. That should be the square root of 4 over 2. And this is the same as 6 plus or minus 2 over 2, which you can as well write as 3 plus or minus 1. So our d1 in this case, you can just say that therefore our d1 is equals to 3 plus 1, which is 4, and our d2 is equals to 3 minus 1, which is 2. These roots are real and distinct, real and distinct. So how do we write our general solution? So you can say that yc is a function of t, remember, is c1 exponential 4t plus c2 exponential 2t, where c1 and c2 are arbitrary constants. Let's get the particular integral. So write particular integral. That is denoted by y subscript p. What is it equal to? You can use three methods. Either of those three methods, you could use inverse d operators, or the method of variation of parameters, or the method of undetermined coefficients. For my case, I want us to use the inverse differential operators. So I'm going to make y the subject of the formula here and operate on the function on the right-hand side. So this is what you are going to get. It will be 1 over d squared minus 6d plus 8. Then on the right-hand side, what did we have? It was 2t times exponential 3t. So here is a product of a polynomial and an exponential function. So what you do is to use the shift rule, exponential shift rule. So let me shift this to the left of the D operator. So remember, we are using use exponential shift rule. Shift rule. So what are we shifting? The exponential function is this one. So our alpha is equals to 3. So we are going to replace d squared, not d squared, but d. Replace every d that you have found by d plus alpha. This means where we have d, we are going to replace that by d plus 3. So that this can now be written as exponential 3t 1 over d plus 3 squared minus 6 into d plus 3 plus 8. This should operate on 2t. Now we remain with the 2t because we have shifted the exponential function. So let me work out the denominator. I'll have this line and write here d plus 3 squared minus 6 into d plus 3 plus 8. What is it equal to? It will be d squared plus 6d plus 9 minus 6d minus 18 plus 8. And so this is the same as d squared. The 6d will cancel. You can see from here, this and this will cancel. So we have 9 plus 8, which is 17, then minus 1, minus 18 is negative 1. So that's d squared minus 1. I hope that is clear to everyone. So let me rewrite this. We'll now have exponential 3t 1 over d squared minus 1 operating on 2t. 2t is a polynomial of degree 1. And so, because look at the denominator, d squared minus 1, you cannot be able to factor out d. This d is not common in those two terms. So we are going to drop d squared. Why? Because the degree of d squared, which is 2, is greater than the degree of the polynomial here, which is of degree 1. So right here, this is a polynomial of degree 1. So we are dropping d squared because 2 is greater than 1. 2 is greater than 1. So we drop the term containing d squared. So that what we have here is simply, now it will be negative exponential 3t times 2t. That's our particular integral. So let's get the general solution. We simply add those two solutions. So right here, general solution. That's equals to complementary function plus the particular integral, or y is equals to yc plus yp, or y is equals to c1 exponential 4t plus c2 exponential 2t minus 2t exponential 3t. C1 and C2 are arbitrary constants. So that's our general solution, but we need to replace t so that we go back to the old variable x. So put where we have t, substitute that with ln x. That means where we have exponential t, that's the same as x. Exponential 4t, exponential 4t, that is the same as x raised to 4. Exponential 2t is the same as x squared. So therefore, y is equals to c1 times x raised to 4 plus c2 times x squared minus 2 ln x times exponential 3t, that is would be x cubed. So this is our general solution. And if you are given the initial conditions, those will help you find the values of C1 and C2. But because in this case, we don't know the initial conditions, we cannot be able to find the values of the arbitrary constants. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving Cauchy Euler equations. Bye-bye.